Hey class, Mr. Moydin here with a final example in this particular set of videos dealing with mathematical finance and for our applied math class. So let's go and dive in. We're shopping around for a new savings account to put away some money. What monthly compounded rate would we need in order to double the size of our initial deposit, assuming no further deposits, in 15 years? So essentially we have one lump sum of money, we want to put it away in a savings account, and we want to figure out what interest rate we should be looking for in order to achieve doubling our account in 15 years. So this phrase right here should clue us into what formula to use, monthly compounding. It's not continuous, so we're going to be using, at some point or other, this formula right here. Oops, that should be a fraction. And let's see what we have in the actual problem. We're looking for the rate. What rate, right? So we don't know that. The time is going to be 15 years. The number of compoundings a year is monthly, so that's going to be 12. And notice that we have no actual dollar amount that we're investing necessarily or saving, right? But we do know that it's going to double, or we want it to double rather. So this idea right here of doubling the size, it tells us that the amount that we extract from the savings account in 15 years needs to be equivalent to whatever the initial principal was times 2. So that's still going to leave us with two variables, right? R is going to be part of our problem because we're looking for it, but one of these two variables has to stick around for a little while, but we'll actually see that's not really a big deal in just a moment. So let's go ahead and plug these values in. The amount we take out is actually going to be 2 times whatever the principal was, equals the principal, which we don't know, 1 plus our rate, which we also don't know, over a number of compoundings, which if it's monthly is going to be 12, raised to the nt power, which is 12 compoundings for 15 years. So we have a variable here for r and a variable here, and that p appears twice, which seems like a problem at first. How do we solve this two-variable equation with only one equation? Normally you'd need the same number. So we can actually reconcile this by simply dividing both sides by whatever p is, in order to find the ratio, which is a number, as opposed to a variable, between the amount that we want to have and the amount that we initially deposit, which, as we know, is 2, because that's what the idea of doubling is all about. Over here we have 1 plus, I'm going to write that as 1/12 r, raised to the 12 times 15. Could do that in my head, but it's a little late in the day. I'm sure you understand. 180. Okay. Now here's where things get a little bit tricky. We have this term raised to the 180th power, and we have a variable inside there. So in essence, right, a much more simple version of this might look something like this. This is what I was trying to allude to in class. A sort of simplified version of this problem would look something like 2 is equal to r to the 180th power. Now I know there's more stuff in there, but bear with me for a moment. To get rid of this 180, all I got to do is take the 180th root of both sides, because that's what a root will do. It'll cancel out the exponentiation. And that will give me whatever the thing being raised to a power, or the base was, right? So this same basic idea is going to allow us to work here. Since I have this stuff here, raised to the 180th power, all I got to do is to take the 180th power of both sides. So let me try to color code this a little bit. The part that I'm putting in red here is what I'm doing to both sides of the equation. And the pencil part is exactly the same as it was there. The net result of taking a power, in this case 180, and taking the exact same power root is cancellation. So the inside part on the right-hand side is simply going to be all that's left, 1 plus 1/12 r. And now in the calculator, we're going to type in the root number first, which is the 180th root. On a TI calculator, math choice 5, 2, is that amount there, 1.00385. I'm going to use this actual value in just a moment. I'm going to subtract 1 from both sides. Again, using the full amount there, not rounding anything. So the rounded version on paper would be this. Equals 1/12 R. Either multiply both sides by 12, oops, can't see that, or divide by 1/12. Two different ways of saying the same thing. I like to multiply by 12 in this case, just to show the monthly impact of it. So multiply this rate by 12, and we get 0.04629 equals R, which is a percentage, which is the way we typically see interest rates advertised. We get 4.629, or about 4.63%. Which, anecdotally, is a pretty high interest rate for most savings accounts. You might see this in what's called a certificate of deposit, or usually other financial instruments. But nevertheless, in order to achieve doubling in 15 years, you would need this interest, provided it was compounded monthly, as it was in this case. Alrighty, hope this helps.